Okay, I'm back to talk about nano-photodetectors. So let's have another more in detail look about the system I described earlier. So you've got the emitter and the receiver. And let's go over what exactly is happening, why exactly we come to this formula. So to start, our emitter has sent us a certain charge Q photonic. That charge is going to be absorbed by the photodiode and is going to result in an input voltage to our first transistor. So what's the input voltage going to be? Well, it's the charge, so the number of photons times the charge of an electron, divided by the capacitance of the photodiode, CPD, and the gate capacitance of our transistor. So that's our input voltage here. Now, we assume here that we are at a given technology node and that the FT of our transistor is given to us. We can't play with that. So that's a given parameter in our problem. So what we're aiming for is to find the right size for this transistor in order to get a certain voltage at the output of our amplification stage to feed into the rest of our system. So the certain voltage we want is also fixed. It's V cents in this derivation. And it's going to be given by this formula. So if you look at this, Vn times the transconductance, that's the amount of current that we're going to modulate with the input voltage and the transistor. This is the length of time during which that current is going to flow. So all this together is the amount of charge that's going to flow and into here, and it's going to load up that capacitance right here. So in the end, this is the voltage that comes out of this transistor. Now, these two formulas, you should know, are classic transistor formulas. And so when you go through put all these equations together, you end up with this formula for the total energy per bit of the receiver that I described earlier. So it's proportional to the capacitance of the photodetector and mostly inversely proportional to the photon charge that is absorbed. And as I've already mentioned, the lower the capacitance of the photodetector, the more energy efficient your entire system can be, because you'll be able to use less photons per bit and your amplification energy also goes down. So, what's low capacitance? Well, in most of today's systems, we use both avalanche photodetectors and PIN diodes as the receivers. So we put the optical fiber here, and here you have the receiver, and it's either an APD or a PIN diode. So these are obviously very big. I mean, you can see them with your naked eye. So they have very large capacitance. In more modern systems, such as what is used by Luxtera, we can have waveguide integrated photodetectors. So here you see a germanium slab, and it's sitting on a silicon waveguide. So I'll go over, this is the Silicon Photonics technology I was talking about earlier. And so your light comes in on the silicon waveguide, couples up to the germanium, and is absorbed in the germanium. So a silicon, you can see the scale here, 300 nanometers. So obviously you couldn't see this with your naked eye. And the capacitance of these systems are much lower. Now, the problem is, here we've got the picture of the entire chip with the amplifier. That's what we derived the energy for earlier. And here is that germanium waveguide detector, which it's not this one, but it looks kind of like that one. And well, what we're seeing right here is that you have to have a wire that's going to bring the signal from the photodetector all the way to the transimpedance amplifier. And what does that wire have? It has capacitance. Actually, the capacitance of a wire is approximately 2 picofarads per centimeter. That's also 200 attofarads per micron. So for every micron of wire, before you get to your transimpedance amplifier, you're adding 200 attofarads of capacitance to your photodetector. And as we showed earlier, that results in the need for huge amplification because your signal isn't going to be very strong, and that means that you're going to burn a lot of energy in the amplifier. So that's not good. Here we go. Capacitance of a wire, 200 attofarads per micron. So tighter integration, I talked about it earlier. We don't want all those wires. So Silicon Photonics is a promising solution. So what is it exactly? Well, we use a standard CMOS technology, and instead of building transistors on the chip, we're going to build optical systems. And we're going to use the CMOS nodes, which would be today obsolete, and because the feature size is much bigger. But for Silicon Photonics, a waveguide is usually 500 nanometers wide, so we don't need the lithography to be that small. And what you see here is that on a chip you can bring an optical fiber, and underneath it, right here, you've got a directional coupler, a grating coupler. And so what's going to happen is the light that comes onto your fiber is going to come here, and all these grates are made so that you scatter light and it all constructively interferes into a waveguide. So you're able to very efficiently couple light from an optical fiber into a waveguide here. And now you've got all this light very, very tightly confined in a waveguide that's about 500 nanometers wide and 220 nanometers tall, because the index of refraction of silicon is bigger than that of silicon dioxide. Additionally, the band gap of silicon is larger than the band gap of germanium. So silicon waveguides at 1550 nanometers are transparent. Germanium, on the contrary, is not transparent. So if you put germanium on one of those waveguides and the light couples into it, you can absorb all that light. So it can travel freely in the silicon, and it can be absorbed in the germanium, and the germanium can serve as your photodetector. So that's why you can build on-chip germanium photodetectors, because we can grow that germanium on silicon CMOS. So, as I said, you can have silicon passive structures on your chip, such as here, this coupler, and here you can have rings to do either add, drop, and a lot of other functions. Modulators also, which are crucial to modulate the light from the laser, and a lot of companies are actually using those today. So what are the challenges? Well, even though germanium absorbs light at 1550 nanometers, it still has an absorption length of 21 microns. That means that light needs to go through 21 microns of germanium before being fully absorbed. So we're going to have to find a way to concentrate the light and reduce that distance, because in 21 microns of germanium, you have the time to build up a lot of capacitance. What's another issue? Material quality. There's a 4% lattice mismatch between silicon and germanium. So when you grow germanium on silicon, and this is what's happening right here, the silicon interface is at the bottom here, you're going to see a lot of defects that propagate through the germanium. So your germanium is going to be full of defects. And that's obviously an issue if you want to make high-performance devices. This is a photo of, you see a scale here, 300 nanometers. Well, actually, this germanium detector is much longer, since you need quite a substantial amount of length to absorb all the light. So what are the solutions? Well, for concentrating light, there's a number of them out there. You can try and build an optical cavity. In this picture, you would have your germanium here and a metal box all around. And if you tune your box right, you can have a confined mode in here. And so you can hope to absorb as much light as possible in a very small amount of germanium. Or you could imagine a 1D photonic crystal system. So for example, you would have light coming in here, and here you would see a 1D photonic crystal, which would concentrate the light to the germanium photodetector, which is right here in this picture. So you could make that germanium photodetector quite small, and you can see a picture here of the idea. You've got the light entering here, and you have a cavity made in the waveguide. Photonic crystal cavity, and here's your your little piece of germanium, and as you can see, the light intensity is strongest right in the center where your germanium is. So you're going to have a lot of absorption. So that's one path towards concentrating light and having smaller photodetectors with smaller capacitance. For material quality, well, there's a technique that's being used more and more, and that's called a rapid melt growth, and which we're focusing on which we're trying to use in the E3S Center. So what does rapid melt growth consist of? Well, you're going to deposit germanium over silicon dioxide and over silicon, and you're going to have just a narrow window over the silicon. So the germanium only sees the silicon crystal here in this area. So you deposit your germanium, you pattern it, and then you cover it entirely in oxide. So you're going to add oxide above here. You're going to have a layer of oxide that completely encapsulates your germanium. And then you ramp up your temperature. So you can see in this graph, you bring the temperature up to above the melting point of germanium. So all your germanium is going to melt, but it's encapsulated in the silicon dioxide, so it can't go anywhere. And then as you bring down the temperature, your germanium is going to recrystallize starting through here. So of course you've got your lattice mismatch going on here, so you're going to have defects, but they're only going to propagate a certain distance. And what's going to happen is that your germanium is going to recrystallize from there, and it's going to recrystallize all the way. And here you can see, here's the seed. So here it's sitting straight on silicon, and here it's sitting on silicon dioxide. And what happens is as you bring the temperature down, your germanium is melted, and it crystallizes in this direction, so that you can get, starting from about here, just one single crystal of germanium, very well defined on your silicon. And this is called the rapid melt growth method, and we've used it to make photodiodes here at UC Berkeley. And it works, and it enables a very good quality of germanium. Okay, I'm just going to conclude on this. I forgot that I was switching. So I thought I was going to have, a little thing with the next slide written. But so I'm just going to say my conclusion for this part, and then I'll switch to the next, okay? Yeah. So now that we've addressed the issues of material quality and light concentration, what can we do in order to actually get an efficient system? And so I'm going to talk now about phototransistors. So I showed that we want to get the capacitance of our photodiode as small as possible. And if there's a wire in the entire system, we're going to add the capacitance of that wire to the photodiode. So if we can get rid of the wire altogether, that would be great. What that means is that we need to integrate the photodetector straight into the transistor. So what we want to do here is have all this system in one unique device. So have our diode and our transistor be just one device. And I'm going to go over different types of phototransistors, and I'm going to go in detail into the bipolar junction phototransistors. So here are 4 phototransistor designs that have been explored in the past. So most of them, all these 3, work on mostly the same principle, meaning you're going to it's a classical transistor, and you activate the gate with photons, or the gate or the source or the base with photons rather than with a direct wire. And then there's the avalanche photodetector, and what the avalanche photodetector is it's a strongly reversed PIN junction with a high enough voltage that photo-generated carriers, as they propagate, as they go to their respective terminals, can ionize other electrons, other atoms. Sorry. Okay, let me restart this. Damn, I should have left that. Okay, I'll start back from from this side. Okay, sorry about that. So here are 4 different phototransistor designs. All of them, all these 3 work mostly in the same way, meaning they're a different type of transistors, but every time either the gate or the base, in the case of a BJT, bipolar junction transistor, is activated with light rather than with electricity. The avalanche photodetector is a slightly different. In this case, it's a reversed PIN junction with a high enough voltage that photo-generated carriers, when they go to their respective terminals, get enough energy to create new electron-hole pairs, and so in that way they are amplified. Because if you start with just say 1 electron and it ionizes an electron-hole pair on its way, well, you end up with 2 electrons. So you've multiplied your current by 2. Now there's several problems associated with each one of these different transistors. The photo MOSFET, what you do is you generate your gate here is made out of germanium, so that's where you absorb your light, and it's very low. It is not very highly doped. So when you bias it, you can deplete it, and what's going to happen is that your electrons, for example, will go down to the contact, and your holes will accumulate on the surface on your oxide barrier between your gate and your channel, and that'll attract electrons, and then you can create a channel, and you've got your photo holes are amplified since many electrons can pass through from the source to the drain. On a photo JFET, you're going to absorb light on a a tiny island on top of your channel, and because of the alignments of the bands between germanium and silicon, so if this is germanium and this is silicon, you've got a large mismatch at the valence band. So your holes are going to stay blocked in the germanium right here. And that's going to attract electrons that are going to be able to go through the silicon channel and that are going to be amplified in that way. What I'm going to focus on today in more detail is the bipolar junction transistor. Bipolar junction phototransistor, actually. So let me get into more details of this phototransistor. So a usual electrical BJT, so bipolar junction transistor, has three terminals: the collector, the emitter, and you would have a connection to the base here. And you can modulate the current that goes from the emitter to the collector by applying a gate voltage, base voltage here. Now for a phototransistor, we're going to take away the contact to the base, and we're just going to have contacts to the emitter and the collector. So let's have a good look in detail of how this works. Now I've taken a cross-section of the device here and drawn the band diagram through the device. So your emitter is highly doped N-type. If you want, you can actually have a heterojunction. So here's silicon germanium here. We'll see what that does later. And your base and your collector, so red and blue. So your base is going to be doped P-type, and your collector is going to be doped N-type. So what you have under no bias is just two back-to-back diodes. So no current can flow through them. So how is this going to amplify our light? Well, for starters, you've got between the base and the collector, you've got a large depletion region. That's drawn here. So you're going to collect, your light is going to shine onto your BJT, and you're going to have electron hole carriers that are generated. The electrons are going to drift down to the collector, and the holes are going to go into the base. And since the depletion area is fairly large, you're able to collect a lot of light that way. So you've got, to start, optical absorption in the base collector depletion region. Now, all your electrons are going to be swept into the collector, where they're majority carriers, and they're going to be carried away. And all your holes are going to go into the base, where they're also majority carriers. But there's no contact to the base, so they're going to stay blocked here. There's a barrier here to get to the emitter, and there's a strong barrier to get to the collector. So your holes are kind of stuck in this region. So that gives you a lot of positive charge in your base, which is going to lower the energy of, which is going to lower your bands. You're going to get a positive voltage and your bands are going to come down. That's going to allow a lowering of the barrier for these electrons that are in the emitter, because your emitter is N-type, to go through the base and down to the collector. So that's the next step. You get injections of electrons from the emitter into the collector. In the same time, your holes are going to see a reduced barrier here, and they're going to be able to go, you're going to get some injection of those holes into from the base to the emitter. And that's how your transistor discharges. Now, in order to get gain, obviously, you need to have more electrons that can go through your base than holes that get injected into your emitter. And this is what we have drawn here. While you have one hole that gets injected into the base, you're going to have several tens or hundreds of electrons that are going to flow over from the emitter to the collector. And that's how you get your gain. let's have a detailed look of what that gain looks like. Why do you get more electrons than holes? Well, the way your electrons go through your base is they go through diffusion. Same thing for your base, for your holes to your electrons. They're going to diffuse until they touch the contact here where they recombine. So first of all, you're going to have in your gain factor your ratio of the width of the emitter to the width of the base. So the shorter the base, the easier it is for the electrons to go through, the more gain you get. The next thing is that your electron is your emitter, is very highly doped N-type, which means that effectively you've got many more electrons here, and so in a way those are going to be there are going to be much more of them to be injected here, whereas your base is p-type and there are not as many holes. It's not as highly doped, so there's not as many holes, and so you're going to get less injection into the emitter. So as you can see here, there's also in the gain the ratio of the emitter doping to the base doping. This here is the emitter of the ratio of the diffusion coefficients for electrons and holes. I won't go over that, but you can find it in any good textbook. Now, this final term here is if ever you have a heterojunction, and you need to make your heterojunction right, meaning, that imagining we had silicon in the base instead of germanium. Well, silicon, as I drew the band gap earlier, has a larger band gap, and most importantly, that happens at the valence band. So if you've got a larger barrier here, you're going to stop your electrons from going through, and that's going to obey the Fermi distribution of your electrons, and so you just get an exponential term of that extra barrier energy over kT, since that's your factor in your Fermi distribution. So that's where your gain comes from. High doping in the emitter, low doping in the base, and short base length, and if you're fancy, a heterojunction between the base and the emitter. Obviously, one of the most important factors here is going to be the speed of the transistor, because we want it to be able to follow very high data rates. So what's the FT of a bipolar junction transistor? Well, you've got obviously the transit time, so that's roughly the time it takes for your electron to leave from your emitter and to make it all the way into your collector. So your transit time is mostly going to be inversely proportional to your diffusion, inversely proportional mostly to your base, the square actually of your base length, because it's a diffusion process, so there's a square here. Also in modern transistors, you actually have a depletion region whose dimension is going to be fairly comparable to the dimension of the base, and here your electrons are going at a velocity saturated speed, so you're going to have to add another factor, which is going to be the width of your depletion region divided by your velocity saturation speed, and there's a factor 2, which I'm not going to go in detail to why it's there, but there is a factor 2. So this is your transit time. So once again, you want to make your base and your depletion region very shallow. And you're going to have your capacitance discharge time. So CBE and CBC. Those are basically the capacitances associated with your two PN junctions here. So you've got one PN, you've got a PN junction between the N and P, the emitter and the base, and that has a certain associated capacitance, CBE, and another capacitance, CBC, which is between the base and the collector. So as we've said previously, we want to minimize as much as possible the capacitance of our detector in order to minimize the amount of energy we need to amplify the signal? Well, even if it's integrated into the transistor, that stays true. So we want to try and minimize, to make as small as possible, the emitter base and the base collector capacitance. So that's why in this depiction, your emitter is actually, and your base are actually much smaller than the entire device itself. And that's to reduce this area right here and here to have a reduced capacitance for the entire system and better speed. So finally, if we can make this in very small dimensions, which is enabled by the fact that we're using the common CMOS technology and we're able to grow good quality germanium on it, and we have light that is very tightly confined into waveguides and we can concentrate it, we can hope to build a very small phototransistor with a very small capacitance associated with it and hope to reach the most highly energy efficient goals that we've set for ourselves. And that's what we're pursuing currently at the E3S Center. So as a conclusion for my part, I would say that the low energy budget link requires a low capacitance detector. That's what this part of the presentation was about. And a high efficiency emitter. That's what Michael talked about previously. And you can see it in the system equations. Now, tight integration of photonics on silicon have enabled to get the photonic systems and the transistor very close together, the receiver and the transistor. We don't need to wire bond external photodetectors to circuits anymore, and we can reduce the wire capacitance. Hopefully fast and low capacitance germanium photoreceivers. So we've built some PIN diodes in the center, which are quite fast and have on the order of femtofarad capacitances, so that's pretty good. As I mentioned, good germanium quality enabled by the rapid melt growth method. And we're looking into potential phototransistors, and we're starting to build bipolar junction transistors all integrated into waveguides and built-in germanium grown with this rapid melt growth method.